Today we're going to talk a little bit about what we are looking at in terms of how to write a chemical equation, a balanced, full chemical equation. So we're going to go through this kind of stepwise. So we talk about a chemical reaction, we're talking about reactants becoming products, right? So the reactants are what we start with, those are the chemicals we start with, the products are the chemicals we end with. We're not creating or destroying atoms in the setup. All we're doing is rearranging the way atoms are connected to each other to come up with new compounds. So we have to write an equation that shows this transformation, right? How do we go from one set of compounds to another? If we think about it in terms of English, we could say something like hydrogen gas plus oxygen gas yields water vapor. That's a brief English description of how water is made, right? If you explode hydrogen and oxygen gas together, you get water vapor that comes out of it. But how do we translate this into the syntax of chemistry? Now, some people argue, why do we have to deal with the syntax of chemistry? Why can't we just say it this way? Well, it comes down to interdependence of different cultures, right? We need a common language by which we can talk about chemistry so that no matter who's talking about it, we're all thinking the same things going on. And this can be really important if you're doing, say, industrial processes where a misstep in it could create tons of poisonous gas that might be released in a setup. So there's a kind of standardized syntax. Now, of course, it's based on European standards because it was developed by old dead white dudes in Europe. So it does have that benefit. If you're an English speaker, it makes a lot more sense. But if you were to go to Thailand or China, they would use this same syntax when describing chemical reactions when they wrote them out. So first thing you do is just roughly translate everything down. Hydrogen gas is H2. Oxygen gas is O2. Water is H2O. Now, of course, the biggest mistake people usually make in this equation is they forget hydrogen and oxygen are diatomics. So don't forget the diatomic elements. When you say hydrogen gas or you say oxygen gas, you're talking about that diatomic form, not H and O. Now we put a plus sign, that means those two are added together, and the arrow means the reaction progresses from the left to the right. Right now, all of our chemical reactions are going to be called unidirectional, right? So they're going to go one direction, from reactants to products. Later on in the term, we're going to talk about what are called equilibrium reactions, which can go both ways at the same time. But we're going to keep it simple right now and just talk about reactants becoming products. So, am I done? No, not yet. Law of conservation of matter says I can't create or destroy matter in the reaction, just rearrange it. So that means on both sides of that arrow, both sides of that equation, I have to have not only the same atoms, elements, but I have to have the same number of each element, right? Indicating that I didn't lose or gain any, I just swapped who they were partnered with. And we look at this original setup we made, and we realize we don't have the same number. Yeah, we got two hydrogens on both sides, but on the left side we've got two oxygens, and on the right side we've got one oxygen. So this is what we call unbalanced, and we need to now balance this equation, right? Now balancing the equation means finding the smallest whole number ratios, right? Whole number ratios for all the compounds so that the two sides balance out. Notably, whole numbers, no fractions allowed at the end, and you want it to be the smallest ones. So if, say, your ratios came out to be 3, 6, and 3, that wouldn't be the appropriate numbers to use because those are all divisible by 3. You would want to use 1, 2, and 1. So don't forget to make sure you're using your smallest ratios when you're done. So how do we do balancing equation? Well, I always kind of think of it as a tick-tock kind of method, that you do something on one side, see what effect it has on the other, see what effect that change had on the original side. So kind of back and forth, tick-tock, from one side to the other. So let's say we add a second hydrogen molecule to the reactants, all right? Well, if we do that, then we've put it farther out of balance because now we've got 4 hydrogens on one side and 2 hydrogens on the other. So what change does that make to the other side? Well, to get 4 hydrogens on the other side, I need 2 waters, right? Now I've got 4 hydrogens on both sides. Well, let's look at the oxygens. Now if I look at the oxygens, the 2 H2Os give me 2 oxygens on the product side. So now I have everything I need. My equation is what we call balanced. Let's try a different one. And again, you could pause the video right now and try to work this out for yourself, but I'm going to go ahead and continue. So H2O2, H2O plus O2. This again would be one of those things I'd ping pong, but I'd go with the oxygen this time, right? Because right now I've got 3 oxygen on one side, 2 oxygens on the other. So if I put 2 H2O2s, which is hydrogen peroxide by the way, on the reactant side, what's that going to cause to happen to the product side? Well, that's going to make me have 2 waters because now I've increased how many hydrogen I have. That also gets me to the 4 oxygen I need to account for the 2 hydrogen peroxides I put on the left side. So again, back and forth, tick-tock, back and forth through the system. Here are 4 examples. I'm going to go through them. You can pause and go through them in stages if you want to try to work them. So the first one's pretty straightforward. I always love balancing equations where I've got just a metal by itself, right? Aluminum, metal by itself. That means it's the last thing I got to worry about. No matter how many of them I need, I just stick the number in front of it. So what's really concerning me is the chlorine. On one side I've got 2, on the other side I've got 3. Much like when I was doing ionic formulas, I just have to make the lowest common multiple of those 2, which is 6. And so when I do that, that means I have 3 chlorines on one side, or 3 chlorine, on one side, and 2 aluminum chlorides on the other. Well, now that means I need 2 aluminums on the reactant side. So balances out. Second one might look familiar from Lab 6, but again, I've got an individual metal, don't need to worry about it till the end. What do I worry about? The oxygen. So I got O2 on one side, single O on the other. I'm going to need 2 of the magnesium oxides, which by necessity means I need 2 magnesiums on the reactant side. Now the third one, a little more complicated, right? Third one's a little more complicated because here I've got a lot of things at play. Best thing to do is just pick one and work through from there. I'll start with the aluminum. If I have 2 aluminums on one side and 1 aluminum on the other, that means I'm going to need 2 aluminum chlorides. All right. Well, that now means I have 6 chlorines on that side. So I go back to the reactant side, and if I have 6 chlorines, that means I need 6 HCl's. Okay. But that gives me 6 hydrogens, so I have to go back to the product side and make 3 H2Os, which gives me the 3 oxygens from the Al2O3. So back and forth. The aluminum gave me the aluminum chloride. The aluminum chloride gave me the hydrochloric acid. The hydrochloric acid gave me the water, and the water finished out the aluminum oxide on the first side. The last one's probably the trickiest. This is what we call a combustion reaction or an organic combustion reaction. Organic compounds are those that contain carbon. This particular one is acetylene, C2H2. And if you burn it in the presence of oxygen, you get carbon dioxide and water. That's what all hydrocarbons produce when they're combusted, and alcohols produce when they're combusted. The problem is it's going to get tricky, right? Because if I do what I did in the previous problem, I say, okay, I got 2 carbons, so I carry that through. That gives me 2 CO2s. And the 2 hydrogen gives me 1 water. That means I've got 5 oxygens on one side. Well, if I come back and try to do that with the oxygens I have on the reactant side, that would mean I have 5 halves oxygen, right? So I need 2.5 oxygens. can't have halves. But there's actually an easy mathematical trick to solve that. If I have 5 halves, I can get rid of the half by just multiplying it by 2. It would give me 5. But if I multiply that one by 2, I have to multiply all of them by 2, which means I would get 2, 5, 4, 2 as my balance. So we're almost to the end of it. The last component of a balanced equation are what are referred to as state functions. State functions are those things that describe what chemical form you have. Now, 3 of them are really easy. Gas, solid, liquid. These are all parenthetical statements that go after the compound, right? So gas, solid, and liquid, G, S, and L. The last one's a little trickier. AQ, aqueous. That means the material is in a water solution. That's what aqueous means, water, right? So if you had, say, sodium chloride dissolved in water, salt water, it would be NaCl, AQ, aqueous, right? So now let's add this all together. Take this one big type of problem. Now I'm going to tell you, these would be a type of problem I would see on the Part B, right? Because it pulls a lot of learning objectives together. It makes sure you can still translate a name to a formula. It makes sure you can write an equation, you can balance the equation, and you can integrate state functions into the equation. So you can expect to see one of these on the Part B, probably a fairly, detailed one. It's a lot easier than me giving you a formula and trying to have you write out what that formula says in English. Trust me, I've tried it. All right? So phosphorus trichloride liquid plus silver fluoride liquid, or solid, yields phosphorus trifluoride gas plus silver chloride solids. So your first step would be to write out each of the compounds, right? So you would need to write out phosphorus trichloride. Well, it's got a tri in it, so that means this is a molecular compound. So I just look for the prefixes to tell me how much of something there is. So it's PCl3. Silver fluoride. Well, I got a metal and a nonmetal, so this is an ionic compound, so I look at the charges to tell me the formula. Silver's +1, fluoride's -1, so it's AgF. Phosphorus trifluoride, same thing, molecular, PF3. Silver chloride, again, same thing, ionic, +1, -1, AgCl. We're given the states, liquid, solid, gas, solid. So we would write it out and we'd balance it, and you should get something that looks like this, right? You'll need 3 of the silver fluorides. That gives you the 3 fluorides on the other side. That 3 silver also allows you to make 3 silver chlorides to deal with the 3 chlorides on the reactant side. Note, the state functions are important. They are the most commonly forgotten thing when people are writing this. The other commonly forgotten thing when people try to do this on a word processor, especially, subscripts. If PCl3 doesn't have a 3 as a subscript, it has PCl with a 3 following it, that's not phosphorus trichloride, right? The subscripts matter. Learn how to use a subscript key on your word processor. Learn how to use a subscript key on JetNet. I've done it a few times in the live sessions to show you guys how to do it. So go back and look at the live sessions, especially for the Lab 6 overview. I go through how to do a subscript in JetNet. So the second one, copper 2 chloride. All right, copper 2 means it's Cu2+, chloride 1-, so the formula is going to be CuCl2. Silver nitrate. Silver's Ag+, nitrate is NO3-, so AgNO3. Both of those are aqueous. They form silver chloride, which we know from above is AgCl as a solid, plus copper 2 nitrate, which would be Cu and then 2 NO3s. Balance it out. I need 2 AgNO3s to give me the 2 nitrates on the product side. That's in turn going to give me 2 silvers, which are going to pair with the 2 chlorides on the reactant side to give me 2 silver chlorides. Common mistake here forgetting the state functions, of course, but also forgetting the parenthetical statement around the nitrate and the copper 2 nitrate. Remember, you can't write CuN2O6 because that indicates something different than Cu and 2 nitrates. So be sure to put your parenthetical statements in, be sure to do your subscripts. You need to be able to do a problem like this. This will be on Part B for this exam. Not these, but there will be a problem like this on Part B for the exam. So that's covering the basics of how do you write a complete balanced chemical equation.